This is a recording of a talk given at the DPS workshop in November 2015 about IRSA. Before I can tell you about IRSA, I need to explain what IPAC is. IPAC is the Infrared Processing and Analysis Center. It's physically based at Caltech, but it really does belong to both Caltech and JPL. Our charter is to support all sorts of NASA infrared missions and archives. We have had a hand in Spitzer, WISE and NEOWISE, Herschel, Planck, some Kepler data, IRSA data, and many more missions and archives. IPAC includes NED, the NASA Extragalactic Database, NASA's Exoplanet Archive, and of course IRSA. IRSA is the Infrared Science Archive. It's one of the biggest pieces of IPAC. Its charter is to be the home to NASA's infrared and submillimeter data. At least 10% of all referee journal articles today use data that ultimately have come from IRSA. Here I have a plot that has the percentage of referee journal articles as a function of time for papers that use IR data. So in 2008, a little bit more than 6% of referee journal articles used, at least in part, data that come from IRSA. By 2014, a little bit more than 10% of all referee journal articles use NASA IR data. IRSA maintains and curates petabytes of images and billions of rows in catalogs. Our priorities are to ingest new data, such as from Spitzer or NEOWISE. We also ingest new processing of older data, such as those from Planck or Herschel, or data contributed by the community. We also maintain the archives so that we can support flying missions, but also make it easy to do new science and prepare for new missions. We also want to enable cutting-edge research by providing innovative tools, supporting the virtual observatory, supporting users that have specific questions about the data that we house. Through us, you can look at the sky in many different wavelengths as a function of time and do big data research on the archives at IRSA. I wanted to highlight that we have a relatively recently redesigned webpage. There are icons on the front that allow you to quickly access the most popular data sets. If you click on More, you can find another row of icons. There is a help desk. You can get in there and search the archive and see if your question has already been answered or submit a new question. There are also video tutorials. If you go to IRSA's YouTube channel, you will find more than 50 videos, including several that are aimed specifically at solar system observers. The videos are organized into playlists, not necessarily meant to be watched serially, but to be used as a table of contents to collect videos on a theme. So there is specifically a playlist about WISE and solar system objects, for example. The bottom line of what I want to try to say today is that we're not quite at the stage of click one button and get everything that we have on your object yet. We have a ton of data, and you can get access to much of it with a common interface. But to really get everything out of IRSA, to get access to all of the pieces that you need, you're going to need to use multiple tools and multiple approaches to search in multiple places, at least for now, to get all the data on your object. There are 3 different kinds of IRSA solar system object searches. I've tried to color code them by theme with boxes here on the right-hand side. So these boxes will appear in subsequent slides during this talk. The first kind is observations that were deliberately pointed at a known object. So the observatory pointed at that object, tracked on that object during the observation. So they were pointed observatories only that can do this kind of observation. You can also search for pre-covery kinds of searches. In other words, given the orbital elements, predict where the object was, and identify where it was serendipitously observed. There's no guarantee that the object was noticed or detected, but it is in that frame serendipitously. The third kind of search is to find pipeline detections that were associated with a known object. So for example, the pipeline processed the frame, identified that there was a source there, moreover, identified that it was a moving object and associated that same object across several different frames with the name of the known object. The key, though, is the object has to have been known at the time of processing. For the 2-mass processing, only about 80,000 objects were known. By the most recent WISE processing, there were 700,000 objects known. So really effectively, this kind of previously known search can really only be done for most objects with WISE. So for the rest of the talk, I'll go through briefly the Spitzer archive, the WISE and NeoWISE archive, a tool called the NeoWISE and WISE co-adder, the tool that's running under the hood to do these pre-covery kinds of searches, which gets you access to WISE, Spitzer, PTF, and NEAT data. I have a couple of slides on Herschel, Plonk, and PTF, and I'll sum up with a couple of slides about FinderChart. Spitzer is an 85 centimeter space-based infrared telescope. It is a pointed mission. So it does not survey the whole sky, it points in specific locations. The cryo-era Spitzer data is entirely archived and there'll be no more changes to those data. However, the post-cryo-era Spitzer is still operating, and we ingest data from Spitzer on about a weekly basis. The two shortest channels of IRAC is what's available with post-cryo Spitzer at 3.5 and 4.5 microns. This is what the Spitzer Heritage Archive looks like. I want to spend a little bit of time on this slide because I want to explain what the layout looks like, because this is the very similar look and feel that you will find in many different IRSA archives. On the left-hand side, you have a variety of searches. Across the top, you have additional options, including help. And in the main search area here, that's where you tell it what to search on and what you want how you want your search results displayed. Spitzer is a pointed observatory, so you can look for pointed observations, but you can also do pre-covery searches. So the moving object search, those are the ones that are pointed observations. In other words, Spitzer was tracking on the object during the observation. The pre-covery search looks for serendipitously caught objects given the orbital parameters. Another kind of pointed observation search is to search by observer, if you know that a particular observer has a particular set of data that you're interested in, or to search by program. So when you click on the moving object choice, this is the interface that you get. You can put in the moving target name on the top. Now remember, this is the target of the observation, not a serendipitously obtained observation, but the target of the observation. It's flexible with what it allows you to put in. You can put in what you want, the moving target name or the NAIF ID, and it will echo back to you what it thinks you've asked for so that you can make sure that it has understood you correctly. Then the bottom part of the search here is where you specify how you want the search results organized. The observation request, or astronomical observation request, or AOR, is the fundamental unit of Spitzer observing. So that's the most compact way of looking at the observations that Spitzer did. The level 2 products are the post-BCD products, in other words, summed up images for mosaics or summed up spectra for spectroscopy. The level 1 data are the BCD data. They're the individual frames that went into the observations. By selecting these tick boxes, we are telling the Spitzer Heritage Archive that we want our results in 3 different tabs, one for each of these categories. So when you do this search on Gaspra, you end up indeed with one tab for each one of the tick boxes that we selected, the AORs, the level 2 products, and the level 1 products. It found 2 different observations of Gaspra, both of which were spectroscopy. The left-hand side and the right-hand side of this screen are linked, so that if you click on one line over here, the stuff on the right-hand side updates to reflect the information about the object you've selected on the left. So in this case, it's telling us that Dale Cruikshank observed Gaspra, and this was his abstract from his proposal. If you click on the other tabs, you can, for example, see the footprint of the observation on the sky. If you click on the tabs over here, you can see a list of the individual frames, and then a tab appears over here that allows you to interact with the FITS files, and you can use tools to interact with the FITS files and to decide whether or not you want to download the data. You can also do an observer search if you want to see what a particular person observed through the Spitzer mission. So we can find that Amy has observed Apollo several times. I can, of course, also do a pre-covery search, which, again, is identifying serendipitous observations of a particular object. In other words, did this object happen to be observed in the process of doing other observations? You can put in the name of your object here, and it, again, echoes back to you what it thinks you've said so that you can be sure that it has understood you correctly. You can also put in the individual orbital elements if you'd like. You also need to put in a time baseline over which you want to search. But be aware that the longer the time baseline you put in, the longer it will take to do the search, because it understands that the further back in time you go, the more uncertain the ephemeris becomes, and so it has to search over a larger area. For this example, I want to search just between August 2004 and January 2005. These are the results. It comes back with the actual individual frames that it found on the left-hand side. And if you can't quite see, there's a green square marking where the object was at that time, here, and here, and here, and here. This is a pretty faint object, so there's no guarantee it was actually detected, but this is where that object should have been at the time of this observation. Let's change gears a little bit and talk about WISE. WISE is the Wide Field Infrared Survey Explorer. It's a 40-centimeter IR telescope in sun-synchronous polar orbit. I have an animation about that in a minute. It has 4 bands, 3.5, 4.5, 12, and 22 microns. It is a survey mission, so it surveys the entire sky in about 6 months. All of the data from cryo-era WISE is permanently archived, but post-cryo-era NEO-WISE is still an operating mission where you can still use the shortest 2 channels. There are several different WISE releases, and so the key to using them well is really understanding what is contained in each release and why the releases are different. So WISE is on a polar orbit. I have an animation here. This is meant to be a representation of the Earth, and this is the swath of sky that WISE is observing on each of its 90-minute orbits. So in one orbit, it takes a series of exposures. On the next orbit, it takes a series of exposures slightly offset. With many orbits, it covers the sky. But note the things at the ecliptic pole get hit on every orbit, every 90 minutes. Things in the ecliptic plane get hit in a series of consecutive orbits every 6 months. So this is what the WISE image service looks like. You can see it looks an awful lot like the Spitzer Heritage Archive by design, because once you've mastered one of these archives, the learning curve for the others is shallower. Just like for the Spitzer Heritage Archive, when you first load the WISE image service, you get dropped into a right ascension and declination position search. But what you want is the solar system object or orbit search. You can put in, again, the object name or ID flexibly, and it echoes back what it thinks you've asked for to make sure that it has understood you correctly. And then you put in a time baseline to do this pre-covery kind of search. The next set of choices that you're confronted with, though, here have to do with what image set you want and what band you want. But the image set is super important, and understanding what it means and why it matters is really critical to being able to use the WISE data well. This is a graphic which is attempting to explain all of the components of the various WISE and NEO-WISE data releases. So here we have a representation of all 4 WISE channels, 3.5, 4.5, 12, and 22 microns. WISE was launched in late 2009, and in January 2010 began its all-sky survey. 6 months later, in July 2010, it had completed one complete sky coverage. However, in August 2010, the cryogen started to run out, and so we lost the 22-band channel first. 6 weeks later, by September 2010, we had also lost the 3rd band from WISE. The 2 shortest channels continued to operate between 3.5 and 4.5 microns. But the spacecraft was put into hibernation in February 2011. So when you have the WISE all-sky release, it covers just those 8 months when all 4 bands were operating. The 3-band cryo release is just those 3 bands. The NEO-WISE post-cryo release is just those 2 bands up until hibernation, which is a little bit more than 2 times the coverage of the entire sky. Now, the all-WISE release is super confusing because it is called all-WISE, which makes it sound like it involves all the WISE data. It is all the WISE data prior to hibernation. So the all-wise release is everything between January 2010 through hibernation in February 2011. But then, in late 2013, NeoWise was reactivated, and it continued to observe in 2 channels. So all of the data obtained in its first year of reactivated NeoWise between December 2013 and December 2014 went into the first release from the NeoWise reactivation, and that was released in March of this year. All the data taken between December 2014 and December 2015 will be included in the second release, which comes out in March 2016. The third year will similarly be bundled as a year and released. So now you have more insight into those data sets or data releases choice. Just for completeness, let me note that the preliminary release data are still available from the first 105 days. Do not use them because they are obsolete. These are the releases that you're most likely interested in. The all-sky 4-band cryo release is just the 4-band data. The 3-band cryo release is just the 3-band data. The 2-band post-cryo release is really the first NeoWise post-cryo mission, and that's just 2-band data. The all-WISE data is all of the WISE data prior to February 2011, which wasn't when it was put into hibernation, co-added or summed up. This is what you want to use for backgrounds or fixed targets. The most recent release is the reactivated NeoWise, and this consists of the 2-band data from the first year of the reactivated mission between December 2013 and December 2014, and the second year's release will be coming in spring 2016. There are different data products that go with each release. As moving target people, you are interested in the exposures and the photometry from the exposures. So the release can contain atlas images, which are summed up or co-added individual frames, and by that process, the moving targets get removed. Then there's photometry obtained from those atlas images. There's also individual exposures and then the photometry from the exposures. The preliminary release had all of them, but that's obsolete. The all-sky release has all of them also. The 3-band cryo release has all of them. The 2-band post-cryo release does not include atlas images or photometry from the atlas images. It does include the exposures and the photometry from the exposures. The all-WISE release sums up everything for the atlas images and the photometry from the atlas images, but it does not include the exposures or the photometry from the exposures because it's all already been released. The NeoWise reactivation does not include atlas images or photometry from the atlas images. It includes the individual exposures and the photometry from the exposures. So this is the result of a moving target WISE image service search. I have searched on all possible image sets for this particular object. So it says at the top that I've searched on this particular object, and that I've searched the all-sky 4-band, the cryo 3-band, post-cryo, and NeoWise R data sets. This is an all-sky derby image, and the little tiny red footprints are the various apparitions of this object that it found for me in the WISE archive. On the right-hand side are the individual frames that it found. So this is WISE 1, 2, 3, and 4 of one apparition, and then WISE 1, 2, 3, and 4 for a second apparition. The box is where the object is supposed to be at that time of observation, and the X's are other apparitions of that object at different times in other data that it found. You can interactively from here search the catalogs, which is a very powerful option. If you click on an individual frame here, it will pre-fill the catalog search with the coordinates of that frame. Then you can search within WISE or any of the other projects at IRSA, and then you can pick which delivery, which data set you want to search. In this case, I've picked the NeoWise reactivation database. Over here, the top catalog is the single exposure source table. In other words, for each frame, the pipeline identified sources in each one of those frames, and that catalog has them all. So the moving object that I care about in those frames is in that catalog. However, since I have an object that is known at the time of processing, A wiser first attempt would be to go to the NeoWise-R known solar system object possible association list. So this is a case where the pipeline has identified the source in the frames, identified that it is a moving object, linked those observations together, and tied it to the name of the object. The big caution, though, is that this is a pipeline product. No human has vetted it, so it may have gotten confused with background objects. So this is why you want to use the WISE image service to do that kind of checking, because the WISE image service allows you to interactively overlay catalogs, explore backgrounds, and identify whether or not the object in that catalog is really what you want it to be. Another way of accessing those catalogs is by not going through the WISE image service, but going directly into the catalog search. You need to pick the WISE category of catalogs, and then you need to scroll down until you find the known solar system object possible association list. Note that there is one of those for each one of the deliveries that included the individual exposures and photometry from the exposures. And you do have to search each delivery separately because the databases are a little bit different. So when you go to do that search, you can search over the whole sky and scroll down to the bottom and use SQL commands to, for example, find all the instances of Neptune that it can find as having been associated with Neptune. These are the kind of results you get. So it has found 2 different sets of observations. This is overlaid on an IRSA image there. It gives you a plot in the upper right, and it gives you the list of the catalog on the bottom. So I have asked it to plot the WISE 1 magnitudes as a function of date. The catalog down here includes all of the rows and columns that it found matching the search criteria that we put in. So overall, for using WISE, when you're doing a catalog search, it ultimately comes back to searching a range of right ascension and declination as a function of time. And you need to look at the individual photometry from the exposures. Unfortunately for now, you do need to search each catalog delivery separately in order to find your object. If you have a known object, you can use the known solar system object catalog, but before doing any kind of detailed work with it, you should make sure that you believe what the pipeline is telling you. If you have a new object or non-Newtonian effects are super important for you, you need to use the Minor Planet Center tracklets to find the right ascension and declination range and then search on that right ascension and declination range. Or you can use the WISE image service to look for apparitions and then go and find the corresponding catalog. When you search from the WISE image service, which is the one that looks like that, it is interactive, so you can interact between the catalogs and the images, and you can search multiple deliveries for images all at once. When you search from the catalog service, which looks like this, that's the one that allows SQL restrictions on columns, and you can do a specific asteroid or comet search. So now, switching gears just slightly, I've covered 2 different interactive services that have a similar look and feel, and the catalog search. But what if you want to add up WISE frames, co-adding individual apparitions of a moving target? Well, then you want to use the WISE NeoWise co-adder. This was originally developed for NeoWise, and it is a moving frame co-adder. You can also use it to co-add a specific right ascension and a declination. You can give it a list of frames, or a solar system object name and a date range, and the distance in the moon or South Atlantic anomaly. And so, for example, you could co-add images of a comet between certain dates. This is what it looks like. If you scroll down, you can see that there's lots of parameters you can put in, such as the distance from the moon and so on. And specifically, I want to highlight that you really can co-add images of an object before or after a particular date. So this is Comet 29P between the first 10 days of May 2010 and between August 10 to 20, 2014. This is on the same grayscale. So the comet really was doing something different at those 2 different times. And this is the kinds of results that you can get from the co-adder. So now I'm going to switch gears slightly again. So we've done 2 different interactive services that have a similar look and feel. We've done the catalog search, and we've co-added WISE frames. Not all the interactive services at IRSA will do those pre-coverage calculations for you, and not all the data sets are currently in that similar look and feel interface yet. There's only about a dozen people working at IRSA. It just takes time for us to get through it. So now I want to show you how you can access directly the routine that is running under the hood so that you can do your own pre-covery calculations with more data sets available. MOST is the moving object search tool, and it is the code that is operating under the hood when you do a Spitzer pre-covery search, a WISE or NeoWISE moving object search, but this is how you access it directly. And just, for reference, some of the PDS services also use MOST under the hood. The main use case for which you'd want to use MOST is to find serendipitous observations of a newly discovered moving target. MOST will help you find the specific data frames you need, but then you have to go get them from the archives and decide whether or not the object is detected and do the photometry. So the MOST interface looks like this. It doesn't yet look like the rest of IRSA. It's on the list. We'll get to it as soon as we can. The list of data sets that MOST knows about include WISE and NeoWISE and all of the subsets of the WISE data. It knows about Spitzer. It also knows about PTF, which is the Palomar Transient Factory. I'll talk more about that in a second. MOST also knows about neat images. We're still working on the mechanism to retrieve the images directly from IRSA, and we have plans to incorporate the 2MAS data as well. Since there's only about a dozen FTEs working at IRSA, please, please, please let us know if you have strong interest in neat or 2MAS or any other data sets getting into MOST. We sometimes need help setting priorities. So if we can demonstrate that there's a dozen people that want 2MAS in MOST, then we have then more of an argument to raise it in the priority list. So these are the kind of results that you get. Here I've searched on Victoria. The blue is the orbital path that it calculated. The green is the regions over which it searched. The red is the images that it found. The images that it found are listed at the bottom. You can save that list, or you can load that list into the IRSA viewer, or in this case, save the images to disk. You can also just save the output and putting into other tools. So now changing gears again, going back to the similar look and feel for a couple more data sets. PTF is the Palomar Transient Factory. It has other slightly different incarnations. IPTF is intermediate PTF. ZTF is the Zwicky Transient Factory. It is using the ground-based 48-inch at Palomar. It has a large field imager on it, and it does mostly imaging in RNG. It is looking for transients, extragalactic and galactic transients, but you can do a PTF search using the pre-covery tool directly in the PTF interface or via MOST. The PTF detections are reported to the Minor Planet Center, so you can search them that way as well. This is what the interface looks like. Again, similar look and feel. You can click the solar system search directly, put in your object and the time baseline and see if it finds anything. This is what I found for Pallas in the PTF archive. Herschel was an ESA and NASA mission. It was a 3.5 meter space-based infrared telescope. It ran out of cryogen already. There's no post-cryo operations possible for Herschel, but you can search the metadata for Herschel here at IRSA, so you can look for observations that it took tracking on the moving objects. For Planck is also a European NASA mission. It did an all-sky survey in several different bands. It has many, many different data products, some of which are time dependent. So you can interact with these data products in a variety of ways using IRSA tools. The last tool I want to talk about is FinderChart. FinderChart is an update of an older tool you may be familiar with. FinderChart gives you simultaneous access to POS, Sloan, 2MAS, WISE, and IRAS data, both the images and the catalogs. Now, as a reminder, these are all surveys, and through FinderChart, you're not searching the individual exposures. And so there's no solar system object search per se in FinderChart, but FinderChart is really good for examining the fields where your object is or is going to be to look for backgrounds. And you can get images up to a degree in FinderChart. The interface, again, looks very, very similar. These are kind of the results that you get. I've searched here on IC 2118. These are 1 degree images. I have overlaid the WISE catalog and I've filtered it so that only the brightest WISE sources appear in the images. So this is how you would go about investigating backgrounds. So just to sum up, there are 3 different ways to search IRSA for solar system objects. You can search for pointed observations where the telescope knew that it was a moving object and was tracking on the moving object. You can do a pre-covery search, which predicts the locations of your object, looks for serendipitous observations. It doesn't tell you whether or not the object was actually detected, but it gives you the frames where it thinks the object is. And then the third kind of search is finding pipeline detections that were recognized by the pipeline as being a moving object and associated together with the name of that object. But the object has to have been known at the time of processing. If you have more detailed questions, I'll be at the IRSA booth during the DPS. There's lots of videos in the YouTube feed. You can also contact us through the help desk if you have ideas for movies. Please let us know. And also, please let us know what additional services or data the solar system community needs IRSA to provide.